Have you ever looked at a bunch of data and just wondered, is there a connection here? Well, today, we're basically going to become data detectives. We're going to uncover exactly how statisticians find, measure, and prove the hidden relationships in the world all around us.
Okay, so here's our game plan. It's a 4-step journey. First, we're going to learn how to literally see a connection. Then we'll figure out how to put a number on it, how to measure its strength. After that, we'll ask the big question. Is this for real, or is it just a random fluke? And finally, we'll use that connection to actually make predictions about the future.
All right, first things first, we're starting with visualization. Before we touch a single formula or do any complex math, we're going to use the most powerful analytical tool we all have, our eyes. I mean, this is the fundamental question, right? Before we can get all fancy with our analysis, we just need a gut check. What does a relationship in data even look like? You know, there's an official term for what we're looking for, and it's correlation. It's really just a simple idea. It's when the numbers in one group, let's say a person's height, seem to move in some kind of pattern with the numbers in another group, like their shoe size. And our number one tool for spotting a correlation is a super simple but incredibly powerful graph called a scatterplot. All you do is take your pairs of data and plot them as dots on a graph to see if some kind of shape or pattern emerges from the cloud. And check this out. These two graphs show the idea perfectly. Over on the left, we're looking at the head width and weight of seals. You can totally see that clear, upward-sloping line of dots, right? That screams correlation. But then look to the right. This one is plotting the heights of U.S. presidents against their election opponents. It's just a random blob of dots. No obvious pattern means no obvious correlation. So seeing a pattern is a great start. But let's be honest, our eyes can sometimes be a little deceiving. To be really scientific about this, we need to go beyond just looking. We need a hard number that tells us exactly how strong that connection really is. And that number has a name. It's called the linear correlation coefficient, but pretty much everyone just calls it R. You can think of R as a report card grade for the relationship. It gives it a score on its strength, and it also tells you the direction. Is it positive with both going up, or negative with one going up as the other goes down? So here's the key takeaway for R. Its value is always somewhere between -1 and +1. The closer your R value is to either 1 or -1, the stronger the connection is. But if that R value is hovering down close to 0, well, that's the number's way of telling you there's pretty much no straight line relationship to see here. Okay, this next part is absolutely critical. Let's say we see a pattern and we even calculate R and it looks pretty strong. How? How do we know it's a real relationship and not just some bizarre coincidence that happened in our data by pure random chance? For example, take a look at this. We've got just 5 little data points here comparing shoe print length to a person's height. It kind of looks like there's a pattern, doesn't it? As the print gets longer, the height tends to go up. But come on, with only 5 dots, can we really trust this? Now, if we run the numbers through some software, it tells us that R is 0.591. That's, not bad. But that is not the most important number on this screen. To figure out if this is a fluke, we have to look at the number right below it. We have to look at the p-value. Think of the p-value as your official coincidence detector. It answers one very specific, very important question. If there was actually no connection at all between these two things in the real world, what's the probability that we would get a pattern this strong in our data just by dumb luck? So for our little 5-point sample, the p-value is 0.294. In plain English, that means there's a 29.4% chance of seeing this pattern just by random luck, even if shoe size and height have absolutely nothing to do with each other. And a nearly 30% chance of being a total fluke is, it's way too high for any scientist to be comfortable with. So the official verdict here is that we have to throw this result out. We just don't have enough evidence to make a conclusion. Our sample was simply too small. But now, watch what happens when we do the exact same study, but this time, instead of 5 people, we get data from 40 people. Whoa. Just by looking at it, you can see that pattern is way clearer. And when we look at the output, sure enough, our R value jumped up to a really strong 0.813. But that's not the showstopper. The real jaw-dropper, the number that proves we're onto something real, is the new p-value. A p-value of 0.000. Now, it's not actually 0, it's just a very tiny number. But what it means is that the probability of getting a pattern this strong just by random chance is practically impossible. This is not a coincidence. This is a real relationship. And that brings us to what is basically the golden rule of a lot of statistics. If you get a p-value that's really small, and the typical cutoff is 5% or 0.05, that's considered statistically significant. It means you have strong evidence to stand up and confidently say, yep, I found a real correlation here.
So, let's recap. We saw a pattern, we measured its strength, and we just proved it's the real deal. Now we get to do the coolest part of this entire process. We get to use this relationship to make predictions. This whole method is called regression, and its only goal is to find the one single, perfect straight line that best cuts through the middle of our cloud of data points. It's like drawing the mathematical summary of the relationship. And boom, there it is. That red line is called the regression line, or sometimes the line of best fit. It's the one line that gets as close as possible to all of those individual blue dots at the same time. It perfectly captures the main trend in our data. But here's the best part. That red line isn't just a picture. It's a mathematical formula. This equation right here is that line. And what that means is we've just built a prediction machine. A forensic investigator can find a footprint at a crime scene, measure its length, plug that number into our formula, and get a really solid prediction of the suspect's height. And really, that's the whole journey. We started with just a messy cloud of dots, and we ended with a powerful mathematical model that we can actually use. We found a connection, we tested it, and we turned it into a tool. So the only question left to ask is, what relationships are you going to go out and discover?